Last time, I received a good amount of feedback on why Quarter-Rate DFE, and the feedback matches what I thought that the Quarter-Rate DFE is becoming not popular. Even though Quarter-Rate DFE's simplicity owing to a single summer in a compact layout without the speed degradation and power overhead. But there are a few caveats we need to pay attention to. Then, more recently, the half rate or even quarter rate is becoming more popular, and we will tell you why. Again, I might have oversights, and I encourage you to please provide your comments or feedback to benefit the Service Design Society. Let's go to the fundamental caveats. What's service? Correct. Serialization and deserialization. Okay. Then, what's the goal of the RX? Right. No error. What's the goal of the RX equalization on top of that? Yes. The goal of the RX EQ is not only to recover the correct serialization data from the TX along with the ISI channel, but also to provide the correct deserialization pair data. Remember that we need to have those low speed pair data operation at the digital logic or processing. If we apply the Quarter-Rate DFE, do you see any pair data in a low speed operation? Of course not. Remember, it's a Quarter-Rate DFE, and you should still see all the serial data without any deserialization. Then, what should you do? Right, just add the demultiplexer after the Quarter-Rate DFE, and that's not a problem. But don't you see the half-rate DFE already performs the demultiplexer demux 1 to 2 at the low speed data rate automatically? Then, you don't need to add extra design or power overhead on the difficult demux 1 to 2. Okay, what's the second caveat in terms of the DFE's input sensitivity? Think about the goal of the EQ image for 5 seconds. Correct. The goal of the EQ is to tolerate as much loss as possible. Then, the input swing of the RX or even the output swing after the CTOE should be small, around 100 mV range. Then, the flow rate sampler of the Quarter-Rate DFE may only have half UI regeneration time, which constrains the maximum data rate. On the other hand, to meet the data rate, the Quarter-Rate sampler may need to increase the minimum RX input swing, which may degrade the input sensitivity over the maximum channel loss tolerance. Instead, under the same input swing over channel loss, the half-rate sampler has twice regeneration time, so the data rate can ballpark go twice faster. On the other hand, under the same data rate, the half-rate sampler might be able to halve the minimum RX input swing or double the maximum channel loss tolerance of the Quarter-Rate DFE. Then, the half-rate DFE outperforms the EQ than the Quarter-Rate. However, there's a third caveat on the clock. Think about the transition image of the clock for 5 seconds. Bingo! May I know if you saw the caveat image of the clock transition here? Great. The clock transition must be as sharp as possible. If not, both the regeneration time and reset time will be eaten timing margin by the transition time. Then either the target speed or the tolerable loss would be degraded. So how do we improve the clock transition? Think about the clock distribution image for 5 seconds. Yes, before talking about the clock generation at the flow rate, the simplest way of improving its clock transition in the clock distribution is to reduce the fan out of the clock buffer. So that's an obvious power overhead. We must pay for it. Unfortunately, there are 2 more caveat images you need to watch out for by sharpening the clock transition. Think about the power integrity PI and reliability image for 5 seconds. Right, the PI issue means a big supply dip or bouncing comes from so many and big clock buffers. To reduce the power supply noise self-introduced jitter, we must add the undied LDO, which also adds more power, area, and design capacity. On top of that is the reliability image. More power from many big buffer and LDO would add the EM concerns in the metal routing of the design, which should add more capacitive plastic to slow down the transition. Even though we pass the foundry's EM rule, the thermal runaway may increase the temperature impacts on the most advanced 16nm to 3nm FinFET device self-heating and aging. According to my design experience in the PCIe Gen 5's 32 gigabit per second, I cannot even make the 32 GHz flow rate clock distribution work at the RCO's post layout nearest over PVT to meet the timing, even though all the EM and aging verification were made and satisfied. Also, I made the LDO to mitigate the PI issue and would add too much power overhead. How was the clock generation? Bingo! The clock generation caveat would be much worse. To generate the 32 GHz clocking, I couldn't use the ring oscillator for reasonable phase noise over jitter. Then I must design an LCPL for the PCIe Gen 5, and I get up the wide tuning range for other protocols over multi-protocol SerDes. Not just that, I must apply an injection lock divider at the first stage of the feedback frequency divider, which has a very narrow locking range and is not very robust over PVT. Overall, I felt the 32 GHz flow rate clock generation was for a limited protocol and cannot be mass-produced. Therefore, I figured out that the flow rate was not good for SerDes IP in multi-protocol use in multi-protocols. Is that really true? If not, what's the caveat image here? Think about the speed image for 5 seconds. Correct. The speed of 32 GHz was too high for a 28nm over 16nm process to apply the flow rate DFE. If the data rate is only 10 gigabit per second, do you think the 10 GHz was an issue or concern for the 28nm or 16nm CMOS technology? Of course not. Therefore, in my multi-protocol design, I could mix the flow rate and half rate in my multi-protocol SerDes. For example, while the SerDes works at 32 gigabit per second PCIe 5 over 28 gigabit per second Ethernet, the DFE was in a half rate mode with a 16 GHz and 14 GHz clocking from Lün-based PO, while the SerDes works at the display ports RBR, HBR, HBR2, HBR3, or 10 gigabit per second Ethernet. The DFE set to 4-rate mode with a 1.62 GHz to 8.1 GHz and 10 GHz clocking from the same wide tuning range Lün-based PO. Here are the summarized image of why we prefer a half-rate over quarter-rate DFE. The fundamental caveat image is the speed under the available process. For example, if the speed is too fast and the process is too slow, there's no way and you must choose the half-rate or even quarter-rate DFE. If the speed is fast and the process is also fast, you need to consider all the circuit caveats like the DMUX, input sensitivity, clocking's SI and PI, metal routing's EM, device reliability, or self-heating issue, LDO overhead, IP robustness, and reusability, etc. If the speed is too slow and the process is too fast, then you must choose the 4-rate DFE. To be realistic, you may have a multi-protocol SerDes, then you want the flexibility to switch 4-rate and half-rate or even quarter-rate DFE in between, depending on the input data rate. Make sense? Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.